Okay, now that we've defined displacement and distance, we can define velocity and speed. So velocity is defined to be the displacement per time, the rate at which position changes. So velocity, v, is a vector quantity, and it is our change in position or displacement per time. So the rate at which our position is changing. The units of this, the units of our displacement are in meters, the units of time are in seconds, and so therefore we have the units of velocity are in meters per second. And it's a vector quantity. So to fully describe velocity, we need both a direction as well as a magnitude. So for instance, 30 miles an hour east, it would be a velocity. Speed, on the other hand, is just the distance divided by the time. So since distance is not a vector quantity, it's a scalar quantity, we have speed is a scalar quantity as well. The units are still the same. It's still meters per second, but speed lacks direction because distance lacks a direction as well. So we use 30 miles an hour east as an example of a velocity. Simply 30 miles an hour would be speed. So oftentimes we'll write the speed of something. Speed is simply the magnitude of the velocity. It's the size of the velocity, just simply how fast without the direction associated with it. Okay, so that is our speed, is the magnitude of our velocity. So for instance here, we talked about previously a particle starting at some point, traveling along some path over here, and coming back to the same point. In which case we said our displacement here was equal to 0 over the entire interval. From the start to the finish, our displacement was 0. Therefore, the velocity in this case, which is going to be our displacement per time, so regardless of how long this takes, since it returned to the same spot, the displacement was 0, and we still have some time, and so the velocity is equal to 0, the average velocity over this entire time interval. So average velocity over this entire time interval from where it started to where it ended is equal to 0. However, the average speed would have been this entire distance divided by the time. So we have the distance, so it would give you some distance in yellow, say it's 2 meters, and say it takes, let's just say here the distance is 2 meters. And let's say the time that it takes, I'll just write this as delta t. The time it takes is, I don't know, 1 second. Then we would have our speed would just be equal to 2 meters per second. On average, we would be traveling 2 meters per second. But our velocity would have been 0 because our displacement was 0. Now, if we took a different point, now that would have been averaged over the entire journey there. Let's say that we were driving along and we decided to stop here for a little while. So we have this point over here that we stopped. And now I want to average my velocity and my speed over now this new time interval and this new distance and this new displacement. Now, the displacement in this case would not be equal to 0. I had some starting point here. So I had a position vector, which was basically at 0, 0. I'll call that my origin. And it displaces, over that time, it displaces to here. So over this time interval, this would have been our displacement. And that would have been the displacement, and then the distance traveled would have been this. And so then our velocity in this case would have been this displacement here divided by however long it took, maybe at only a half second. So whatever this displacement is divided by the time. And so that's the definition of velocity and speed. Oftentimes, actually pretty much always, we're going to talk about our velocity in terms of components. So although the definition of velocity is displacement per time, it's going to be much more useful to talk about it in components. So just like we broke our displacement into components, we had an x component and a y component, an x displacement and a y displacement. We can talk about an x velocity. So the velocity in the x direction would just be the x displacement per time. Okay, so it's how it moves in the x direction divided by how long it took to move there. And then the velocity in the y direction would have been equal to our displacement in the y direction with time. Okay. Another little note here. You'll notice that displacement is a vector. It's always a straight path from one to the other. We have this was our displacement. The distance will always be greater than or equal to our displacement. So if the path is curved, the distance is going to be greater, right? The only way that our average speed would be the same as our average velocity is that if we traveled in a straight path. Okay. Also note here that the distance can never be negative, right? We can never have a negative distance. However, we can have a negative velocity. So if I define a coordinate system like so we define a positive x direction to be to the right and a positive y direction to be upwards, then the velocity as it travels, let's just consider the x component for now, but as it's traveling along this way, it would have some positive velocity in the x direction, right? Because it's traveling off to the right. But over here, it has predominantly a negative velocity in the x direction because it's traveling to the left. So the velocity can be positive or negative, and whether or not it's positive or negative depends on our coordinate system. Okay, so let's talk about just one-dimensional motion for a moment. So let's just say I have a positive x direction is defined to be this way. Now, if I have a particle which moves starting over here and it starts moving off to the right, this would be considered a positive velocity because its change in its x position is positive. Time is always positive, so the sign will be the same as the sign of the displacement. So a positive change in the x position will be a positive velocity. When it turns around and comes back, it will have a negative velocity. So the positive or negative depends on the direction it's moving, and that follows from our coordinate system. If I flipped my coordinate system around and called a positive x to be to the left, then we would have, well, when it's traveling off to the right, this is now a negative velocity. So we have a negative velocity right now, and it turns around and becomes a positive velocity. The positive meaning, in this case, that it's traveling to the left. This will be very important when we start talking about throwing things up in the air, etc. If I call a positive y direction to be upwards, so we have, this is our positive y. Let's say I have a ball thrown up in the air. Then as it travels upwards, its velocity is positive. And then it's going to reach some point and it's going to turn around based on the observations we made in life. So it had a positive velocity on its way up, and it has a negative velocity on its way down, right? And this is based on our coordinate system. Again, if I flip the coordinate system around, so that way I call downwards y to be positive, I would say while it's traveling upwards, it would have a negative velocity now, and then as it goes down, it ends up having a positive velocity. So positive or negative are based on our sign convention. Okay, but velocity can be positive or negative. Speed can only be positive because we can only have a positive distance. We can't go a negative distance. Just doesn't work. Lastly, I talked about an average velocity. up here, this was kind of averaged over this entire time interval going back to this path. Actually, let me redraw this path down here, or another path. So let's say we have a starting point here and we travel along something like this. Now, the average velocity over some time interval, I need to define that time interval or define that displacement. I take my average being my total displacement divided by my total time. So if I'm interested in finding, what is my average velocity from here to here, then I have, this is my displacement divided by however long it took to get there. But I could have, that would have been an average velocity over that time interval. When I traveled there, I could have started out going very quickly and then slowed down a little bit and then sped up and slowed down, etc. So I might be more interested in finding out what is my, could I, if I'm driving, can I make it around a curve? Am I going too fast to make it around this curve here? I might be interested in my velocity at that moment. In which case, I could say, all right, well, why don't I take an average velocity from here to here, in which case this becomes my displacement. Still, that didn't, that considered all this back here as well, right? So if I want to know, I'm interested in just the curve here, I might take 2 points. I'll kind of zoom in on this curve here. I might just take 2 points on this curve that are incredibly close together. If I take a point here and a point here, and I find my average velocity between these, then I have some displacement. It displaces from here to here, and I have some very short time interval. But now I get much closer to my instantaneous velocity. So this is the idea of getting instantaneous velocity. So what we actually do, the definition of instantaneous velocity, and I should have actually said here average velocity. Let me get a little bit more precise in my definition here. Average velocity is my total displacement over my total time. My instantaneous velocity, which we actually just denote with a v, and unless I say average velocity, I'll actually be talking about instantaneous velocity. We'll predominantly 99% of the time talk about instantaneous velocity in this course. So I'll just use v for instantaneous velocity. And what this is, it's defined to be, actually this is some terminology from calculus, but if you don't understand it, it's okay. The way this is written out is this is the limit as this time interval, delta t, goes to 0 of the change in position with time. All this means, like I said, don't get caught up in the notation if you've never seen this before. All this means is I'm putting the 2 points closer and closer and closer together such that basically one point is a nanosecond after the other one, and then I get an average velocity between those two very, very close points, which is exactly what we did up here. We took 2 points incredibly close together, and we just took an average velocity between those 2 points. So this is how we define our instantaneous velocity. It's same as how we define average velocity, but we just put the 2 points really, really close together if I'm looking for the velocity at a particular instant.